All right, welcome everyone. It's 1 o'clock, and we're going to start our summer school lecture for today. I'd like to introduce our speaker today, Darby. He's a PhD student here at the University of Michigan in our detection for nuclear non-proliferation group led by Professor Sarah Posey. So I'll hand it over to him, and he'll be talking about simulating radiation detectors today. Enjoy.
Thanks, Ricardo. And as another note, this lecture will be a little less dense than Dr. Clark's Monte Carlo lecture yesterday, so please feel free to ask questions in the Q&A as we're moving along. I'm happy to take them in stride. Ricardo will be looking at those as they come in and filter out anything that's relevant to the presentation. So thanks again, and we'll start off. So yeah, as Ricardo said, we'll be talking about simulating radiation detectors, and we'll dive right in. As an overview of what we'll talk about today is we'll talk about random walk, which we mentioned yesterday, but we'll repeat that for those that weren't attending or that just need a bit of a refresher. We'll talk about some of the different types of radiation detectors, the simulation softwares that we can use for radiation transport. There's several versions of MCNP, which I'll go into in a few slides out there. There's also GEONT4 and several other programs. We'll be talking about a simulation pipeline. So we'll go from briefly radiation source particle generation. Then we'll go a bit more into particle tracking. There's several modes out there for particle tracking. I've sort of color coded them for you, but in MCMP 6.2, there's PTRAC for particle tracking. In MCMP X, there's an add-on called Polemi that produces the collision data file. That's one we use in our research group here, and I'll go a bit more in depth to today. And in GEONT4, there's also event tracking. And there's, again, several other modes that you can use for particle tracking, but these are some of the bigger ones or ones that I'm familiar with, at least. We can also, once we track our particles, we can scale that to a real measured detector response and experiment through a process called mock pulse processing. In PTRAC, there's a function that's quite simple. It's just an F8 tally, one where you can directly model a readout spectrum for gamma ray detection. And then for Polemi, we can process our particle tracking with this software called MP Post to make it a bit more analogous to the detectors we use, which will be specifically organic scintillators for this lecture. And then also in MCMP 6, they've come out with something similar to MP Post, but that's still in development called Drift. And that applies to the PTRAC and MCMP 6.2 transport. So yeah, there's quite a bit that we could talk about today. I'm so happy to take questions, but we're going to go specifically into just one example for an organic scintillator. And when we get an MP Post, we'll talk a bit about how we do light output modeling for this scintillator. You can see just a plot of the random walk there, a couple detectors and some logoing for MCMP 6, GEONT4. This is sort of our goal here. You see a huge detector called ALICE that they use at the Large Hadron Collider, but it shows all the tracks of ions that collide within ALICE. I see a raised hand, but if you could please use the Q&A, we'd appreciate that. But this large detector volume, you can see several particle tracks here. At the ALICE facility, we'll go to a much more simplistic case, but it's sort of a fun plot to show for how you can track particle tracks with, they're specifically using GEONT4 here, which is a very custom software that I'll go into briefly. To start off, let's review random walk. Specifically, we'll talk about a neutron random walk. In this case, it's that neutral particle that can be released from fission, alpha N, as you've learned in the past few weeks, and some other sources like fusion. When we simulate collisions for the neutron is when it collides with the nucleus. And we define the total cross-section with several sub-cross-sections for different reactors. These macroscopic cross-sections, which are the microscopic cross-section simply multiplied by the density of the material you're considering. If we sum these cross-sections and we normalize them, we can normalize them by the total cross-section, and then we can create these sub-probabilities of each collision or interaction type. And it's sort of given just by this fraction of the total cross-section. We can construct a step function for the cumulative density function of collision events, which we show here. We're only showing 3 reaction types in this case. What we show here is neutron elastic scattering, neutron inelastic scattering, and neutron capture. And in this case, if we are in this 0 to p sub n regime, then we would have an elastic scatter. If we are in this between regime between these two probabilities, so we have the probability for an elastic scatter stepped on top of the probability for elastic scatter, then we would see an elastic scatter event. And then above this, between the inelastic and capture bounds, we would see a neutron capture. To briefly review detectors, so we can simulate, we were talking about a neutron, but we can simulate any particle in a detector. There's several detectors we could talk about today. I couldn't possibly cover all of them, but just to review a few. For gamma interactions in a detector, we're considering the photoelectric effect, specifically Compton scattering in this case for an organic scintillator, and pair production. For neutron interactions, we might consider absorption and elastic scattering, specifically elastic scattering for our organic scintillator. Slow neutrons are typically directly absorbed, while fast neutrons are scattered or moderated to absorption. Gamma ray detectors we could consider are scintillators, semiconductors, and ion chambers, as well as a handful of others, but those are some of the bigger categories. Neutron detectors, we can also consider scintillators, gas proportional counters, and a few other types of detectors, but those are the main two. As you can see, some examples here of photoelectric effect, Compton scattering. We can also see for neutrons, elastic scattering, as well as neutron capture that causes this lithium capture reaction, resulting in alpha and a triton. And a few detector types. You see a scintillator there on the left with a photomultiplier tube readout, and a gas proportional counter with the appropriate electrical readout as well. We have to build a bit before we get into the nitty-gritty of particle tracking. I want to give you some background to what the different types of simulation softwares are. Dr. Clark talked about Monte Carlo in general, but didn't really go into the whole MCMP history. I believe he showed this same plot, which is the history of MCMP. But I want to go a little bit more into that. There was the Great Schism in about 1996 here, where MCMP split into two softwares. It's been continually developed mainly at Los Alamos National Laboratory. And at one point, there was a split between looking at K effective and looking at the physics of a nuclear reactor and modeling more exotic cases like astrophysics and specific detector response for experiments. So MCMP in one track, you see it splits to MCMP 4B and MCMP X. MCMP X is more of those exotic scenarios and looking specifically at detector response for a lot of unique scenarios. And that's what we will go into depth a bit for here, since Polemi was built on this MCMP X branch, but also on MCMP 4B, 4C, and MCMP 5, focusing more on that eigenvalue K effective, the criticality modeling for nuclear reactors. All these MCMP softwares are export controlled, and I know we have a fairly international audience in attendance here. You can request the software, but unfortunately, as an international candidate, you are less likely to be able to gain access to an export controlled software. Unfortunately, I'm not an expert, but one software that is open source is Geant 4. And that's a bit of a learning curve since Geant 4, there are some scientists and computer scientists out there that have already compiled some basic radiation detector simulation toolkits. But it's a bit of a learning curve. You have to sort of get the source code, compile it for your specific scenario, and then you will start to have your particle tracking or experiment modeling capabilities, which is what they do out at CERN. They sort of create their own Geant 4 compilations for different experiments. But MCMP just comes prepackaged. It's an executable, and it already has all these features built in. And you can sort of go and customize it yourself without having to know how to compile code. So Geant 4, as I said, you have to be a bit of a computer scientist to use it, but it can have very similar capabilities to MCMP. And if you are really ambitious, you can start from scratch and you can just start modeling the random walk on your own. We've described the random walk yesterday, and I'll describe it a little bit more today. But if you model the random walk process with a code and use random sampling, which is built into a lot of different programming softwares, you could write your own tracking code. It'd be a large undertaking, but it's definitely possible. Everyone has that capability. So to outline a bit what we're going to go on for the rest of the lecture is we'll talk about radiation source particles and transport, how the Monte Carlo random sampling is evolved. We'll talk about detector interactions in detector volumes. And then from there, from these pure interactions, we're not yet at what we might see in experiment. We have to do some sort of mock pulse processing to completely mimic what we might see in an experimental detector response. So we'll talk about that briefly as well. I see 2 questions in the Q&A, so I'll take a quick look before I move on. OpenMC is also an open source software, which I have used. Yes, that's true, Abhishek. You can definitely use OpenMC. I'm less aware of what detector response modeling has been done in OpenMC, but there's definitely radiation transport modeling that I've seen complete in OpenMC. Yeah, so that was asked anonymously as well. I think I answered that. I'm unaware of detector response in OpenMC, but I'm sure you could have the capability. Like I said, you could write a detector response code from scratch, but it's all about how much time you have to invest and what resources you have available. So we'll start off again with the source particles and transport. And this slide is quite dense. It's pulling a lot from Dr. Clark's lecture yesterday, but in order to start off with radiation detection, we have to simulate a radiation source. So in a lot of scenarios, all you need for some simple laboratory experiments are a monoenergetic point source, sometimes dual energy, but typically it's a well-behaved laboratory source. And all you need to simulate is the emission angle because you're always sampling the same energy. Typically it's isotropic. It can be anisotropic. Isotropic is easier to define. Anisotropy is a bit more involved in source definition, but you can derive the correct cumulative density function to sample if you create a probability density function that correctly reflects the anisotropy. A lot of the times, like I said, a simple source definition will suffice. We can go through, and you saw yesterday the probability derivation for simulating the direction. So you can use 2 different random variables. We show the same here. We show Cassie twice, but it's Cassie _1, Cassie _2. So there are 2 separate random numbers that you generate to get the azimuthal and axial, or I'm probably saying that wrong. Ricardo would know, but to get each direction, the phi and the theta angle. For more complex sources, you might be distributed about a volume. We talked about the example of randomly sampling this square to get this irregular volume yesterday. You can do the same thing with a source generation. If you have a source, let's say you have a melted down reactor core that you're trying to simulate because you want your robot to go inside Fukushima and you want it to be able to measure the radiation, or sorry, withstand the radiation inside of the Fukushima power plant so you can clean it up. You're going to be approaching a melted core that's some irregular shape. Maybe you have some pictures where you can model it, but it's going to be a rough sketch. So you create your rough sketch and then you just sample a square around it. Anytime you're inside this irregular volume, you model a source emission. Anytime you sample outside the target, then you don't actually simulate a source particle. So you can start to implement more complex volumes with intuitive Monte Carlo sampling processes. You can also simulate the energy spectrum. So if it's not monoenergetic, maybe you're dealing with a fission source, which we see the prompt neutron spectrum here. It's a continuous distribution of neutrons or even gamma rays that you might see from the source. Since fission itself is a fairly random process, it's not the same for every fission event. So then you can sample this energy spectrum to closely model what you might measure in an experiment. There's other sampling that you can do as well. We see argon dense plasma emission on the right, which is the photon energy for this specific plasma, which has a quite irregular distribution, several peaks, and then some continuum below the peaks. So you can get quite crazy with your source definition, but essentially it will just be a histogram that you're sampling from with specific probabilities like those step functions we talked about earlier. You can also sample for things like multiplicity, which we won't go too much into today, chain reactions, and other types. Once we define our source, we can go in and conduct radiation transport with some more Monte Carlo. When we generate our particle from the source, it's going to have position, energy, and direction. These cross sections, these macroscopic cross sections we described earlier, are going to be dependent on all three. The position it's produced might affect what type of material you're in, and the direction is going to affect what material your particle is going through. So both of those affect your macroscopic cross-section generation, and the energy, your particle energy, will affect your microscopic cross-section. So that will change your macroscopic cross-section. It's energy dependent. So once you have these three parameters, you can know, okay, now I can generate my macroscopic cross-sections. You create your distribution, your step function that you sample, and then you grab your random number and you figure out what type of interaction is going to occur, if any. Sometime you will simulate this up to the material cell boundary. If your actual flight path ends up being longer than the boundary, then either you're going to end the problem if it's outside of your problem space, what you're concerned about, or you're going to have another volume or cell that you've simulated after that boundary, and you have to resample, and this process continues. So we're random walking, and eventually we're going to make it to our detector here. I see another question, and I think Ricardo is unmuting.
Yes, I was about to say, you have a question on emission angles.
Yeah, thanks. Modeling the radioactive properties of regular sources makes sense to me, but I don't understand what it means to simulate emission angles. Aren't particles emitted from any source along random vectors? William, that's correct. They are essentially emitted randomly. You know, it could be isotropic or anisotropic, so there is still a probability associated with the emission angle. But we are random sampling for this direction. So we're doing our best to model that random behavior. I hope that fully answers your question. If not, please ask a follow-up, but we'll continue on with the random walk. So actually, sorry, I think that fully summarizes the random walk. Like I said, we've sampled our step function. Eventually, we've gotten to a particle termination. One of these cells from the random walk could be our detector. And our detector, we want to know what interactions are occurring, so then we can model our detector response. So in order to do this, we have to track the particles. There's several ways to do it, which I mentioned at the start. In MCMP 6.2, which is the latest distributed version of MCMP, includes ptrack, which is just particle tracking. It can be quite comprehensive, but you have to sort of customize it to get the output that you want. But there's also built-in tallies, which are just summaries of interactions on the geometry. They don't tell you particle by particle what has happened in your geometry, but they give you a summary of your total simulation, what type of interactions have occurred per particle simulated. So that doesn't mean a ton to you yet, but we'll go into a little more specific examples. There's several flavors like surface or cell tallies, where you can model the current, the fluence, energy deposition, pulse height, etc. We'll talk quickly about fluence and about pulse height. The manual for MCMP 6.2 is actually publicly available. So if you're more curious about these different types of tallies, you can go into the manual and sort of learn some applications and examples. If you do not have the software, unfortunately, you can't test it out, but there are some examples there that give you the outputs and plenty of research papers that have used MCMP. In MCMPX Polemi, which is what we like to use at our research group at the University of Michigan, you get a collision data file, which is actually built directly off of ptrack for the MCMPX version. It's just a bit more of a prepackaged summary of collisions in a specific cell that you specify, and that cell could be your detector. And we'll go a bit into what that output looks like for Polemi. In GEONT4, you can also use event tracking, which unfortunately I'm less familiar with, but I know it is a possibility. You can event track your particle and produce similar outputs. And like I said, you can build one on your own. We're not going to do that in this case, but you do have some of the tools with random walk to do that. Now that we've talked about the source and how and what the different capabilities are in codes. We'll talk about the detector interactions. For MCMP 6.2, this F4 tally, it is cell fluence, which can be scaled to a reaction rate. It records the number of particles per unit area, normalized over or averaged over the cell volume, and its specific tally on the model detector volume. In this case, we're looking at like an EJ309 liquid. You could take this volume and specify an F4 tally on it in MCMP 6.2. If you specify the correct reaction type, you can scale the fluence by an energy-dependent macroscopic cross-section. So that's the key part there, is built into these tallies. Instead of, so you are simulating using the macroscopic and microscopic cross-sections, which are energy-dependent. MCMP is just going to give you a summary of what has happened per unit particle simulated. If you want to look at a specific reaction type, it's just going to tell you the fluence tally without this reaction type specified. It will just tell you how many particles have passed through your detector. Okay, but that doesn't really tell me a ton about their detector response. If I'm looking for a specific reaction type that would produce my detector response, then I can apply this reaction type, which will then scale my fluence to more of a reaction rate. You can equate this to count rate with some sort of energy thresholding that's equivalent to your detector, and just model raw count rate. I'm not showing a specific example here. We'll go more into the polemic collision data file and some examples that we can share. But this is how you might model with an MCMP 6.2 F4 tally, the cell fluence to the reaction rate. In this case, we have an organic scintillator. So really, if we were to model gamma ray response, this is just a plot out of null here. If you aren't familiar with null radiation detection and measurements, it is the book. If you want to learn about radiation detection and measurements, we give some great summaries in this lecture. But that book will teach you everything that you need to know, even a little bit for simulation. This organic scintillator is quite a low Z volume. It has hydrogen and carbon. So our Z value only goes up to 6 and is closer to 1 on average. It's going to be very Compton scattering dominant if we're looking at gamma ray interactions, just because it's a low Z compound. So we might look at F4 tally for Compton scattering and then scale that to our detector response. We're going to actually get more specific with particle tracking and polemi, but this is one way you could go about it. I see another question in the Q&A. Re-emission angle model. Yeah. So a particular unstable nucleus. Sorry, I'm just going to read this through before I say it aloud. Yeah, William. So we are getting fairly specific here, and it's actually going to get a little bit out of my expertise, but he's asking, will particular sources have anisotropy or isotropic behavior? So isotropic behavior, to reiterate, I may not have stated, means you're equally likely to emit a particle at any angle from a given source. So if you have a source at a point, it's going to have an equal probability to emit a particle in any direction. As you start to get a larger source, he's asking if it would become more anisotropic. It really depends on the geometry and depends on the composition of your radiation source. Without being more specific, I would say yes, larger sources can have anisotropy, but they can also have isotropic behavior. It just all depends on what the consistency of the volume is. If you had an irregular volume and asymmetric volume, you would probably have anisotropy. If you had a very symmetric volume, you would probably be more likely to have isotropic behavior. When we talk about different sources, we talked about neutron sources. Those sources, like fission, are actually anisotropic on a single event scale. So you're more likely to have, I believe you're more likely to have neutrons emitted along the fragment directions than you would say perpendicular to the fragment directions. Okay, so I'm going to go ahead and dismiss your question, but thanks for the question, William. And we'll move on from F4 tally. Continuing on detector interactions, we're going to go more specifically into the organic scintillator. The example we provide here is for a DT neutron generator, so that's 14 MeV neutrons. We're going to produce an MCMPX polyimide collision file, and it's active interrogation on highly enriched uranium. So we're inducing fission, 14 MeV neutrons on HEU, inducing fission and being detected in our detectors. And sorry, the numbering is off here. I need to update that. The collision file is recorded for adjacent plastic scintillators. And this is the result we might see for those detectors detecting this scenario, this active interrogation scenario. Lots of data here. There's this history number, which is source histories. So each time you simulate a particle from the DT generator, so a 14 MeV neutron, that is going to be one history. You see on history 16, particle number 97 was a neutron, and it interacted, I see here, by elastic scattering, and it scattered on hydrogen several times, the same particle several times. The cell number was 2, which was our detector cell, and it tells me the energy deposited, what time it interacted. So time 0 is when the source is produced. It has to fly, cause an active interrogation event, perhaps, and then it will be detected in our detector. It tells me exactly where in my simulation geometry the detection occurred. So you have energy, time, position, and the weight and generation number. So if it's generation 0, that means we detected a neutron directly from the DT generator, because there's not any generations per se of fission. But as soon as fission happens, we have an absorption, and this fission reaction will release subsequent particles that are simulated. So we might have a first generation fission, a second generation fission, or even a third generation fission. And that's what this is denoting here. So you can get quite a wealth of data from the MCMP collision file. It'll tell you how many times the particle is scattered. It's scattered 9 times here already. And then the code is a little bit more cryptic. We won't go into that today. So we've talked about the detector interactions, how we get those, the polyimide collision file. Now we'll go into some mock pulse processing and talk briefly about detector response. We talked about that DT generator situation, which we will go back to briefly, the neutron response for an organic scintillator. Feel free to ask any questions. But now we're going back for the same scenario I described earlier for the self-fluence tally. And now we're, instead of using the F4 tally, we're going to use an F8 tally in MCMP. And with the F8 tally, we can simply look at the gamma ray interactions. Unfortunately, F8 does not work for neutron interactions. And the reason being is that neutron interactions are not directly scalable in most detectors. Gamma rays are. You'll hear a bit more about that at the end of the lecture. But gamma rays work well for the F8 tally. And we're just looking at pulse height deposition in this organic scintillator. Okay, I see a question in the Q&A. Thank you. Great question. What is a shake equivalent to in real time? So if we go back to this slide, you see that time is in shakes. This is a very MCNP thing. It's not particular to anything else I've seen in class. It looks like Ricardo's typing an answer, but I'll go ahead and answer it for him. A shake is 10 nanoseconds. So it's 10 to the -8 seconds. That causes a lot of issues when you're scaling if you don't pay attention to the time units in MCMP. Don't ask me why shakes is a unit for MCMP, but it's just something that we use. MCMP, as you've seen before, has been around for a while. It's been around before the start of real digital computers. They used physical input cards. So there could be a wealth of reasons why shakes are the units. Maybe it worked better for their physical card system that they were using, or something of the like. But yeah, don't pay too much attention to the time unit. Just know that these codes can simulate time dependence, and it's down to the precision of sub-nanoseconds. So going back to this gamma ray response, we're looking at gamma rays in an organic scintillator, and this is a point for anyone in the chat if they want to chime in. We are looking at the gamma ray response for an organic scintillator. is there anything that we're missing in this gamma ray pulse height distribution that you remember from earlier in the gamma ray week? I'll let you answer as I'm explaining these interactions. And I did give a clue in the earlier slides, but I'd be interested in your response in the chat. The F8 tally here, what it does is it takes these radiation interactions, which are in an organic scintillator majority Compton scattering. We see the Compton scattering curve in several different distributions. We see our measured distribution in blue, so that's what we would assume is the ground truth. The simulation with resolution and the simulation without resolution. So MCMP with the F8 tally can almost directly model the detector response without resolution. We see in blue the measured detection, and in red this weird peak that occurs before that starts to match up again. The reason that's occurring, we're seeing a higher magnitude at the start of the simulation with an uncertainty almost, and then this huge peak that's far separated from measured spectrum, and then we start to match up again. The reason this occurs is truly what we might see in in physics is this distribution occurs and then just drops off immediately. That's what a Compton curve might look like. In fact, if we had a lower energy threshold, it might go all the way down to here. Sorry, my drawing is not the best. But our detector has an associated light output resolution, which also is equivalent to an energy resolution in this case. So we have to add some sort of broadening term. And once we add this broadening term, the black distribution simulated agrees quite a bit better with the measured distribution with a bit of a higher uncertainty. I didn't see any responses in the chat, but I would challenge you for one more question. Sorry, I need to turn off my annotations. One more question would be, why do we see interactions above this Compton edge energy? If anybody remembers our Compton scattering equation, there is a maximum energy deposition for a gamma ray in a volume. Why would we see light outputs or pulse heights above the maximum possible Compton scatter? So I'll leave those as open-ended questions in the chat. But otherwise, I'll move on to the next problem and look forward to a response or two. So that was one way we could get to this sort of mock detector output. But other ways require a bit more processing. We can directly equate gamma rays to a detector response when we're looking at this gamma ray energy spectrum, as I showed for the organic scintillator in the last slide. The neutron interactions and maybe a more complex detector might not be as straightforward to model. In MCMP 6.2, these mock pulse processing modules for P-track, Drift is in development, the detector response function toolkit. You can see the response for an organic scintillator to a sodium-22 source on the center plot, and the drift simulation agrees quite well with measurement. So that's similar to the plot we showed below, but instead of going directly from a tally, you would be going through the particle tracking, which looks at every particle collision and then scaling it to this energy response spectrum. You can also do a quite interesting function called pulse shape discrimination, which this is just showing you the interactions, I believe, for a gamma ray source here. So we do not see two bands, but for anyone that attended the neutron detection lecture, you probably saw neutron and gamma bands for our organic scintillator, and Drift is striving to be able to model these pulse shape discrimination distributions. For Polemi, the processing is quite similar, except instead of looking directly at P-track, we are looking at the collision data file, which I described earlier. You can use this software called MP-Post, which is open source. You can ask for that yourself. If you look for the manual and look for the contacts, you can ask directly for the MP-Post software. We actually have a Python version that's in development here that we hope to share soon as a Python suite. But we can process the simulated data file into a scale detector response. And you see a model here that was then used to produce this pulse height spectrum between simulation and measurement for a mixed oxide fuel. Again, you can write this on your own with some concepts we'll describe here, but it is nice to have a package available. So going into mock post-processing MP post, we talked a little bit about organic scintillators, seeing Compton scattering for gamma rays. For neutrons, there's going to be different types of interactions. There's going to be elastic scattering. There's also going to be fission, but both the photons and the neutrons can inelastic scatter, and both of them can be captured. When you have these reactions, the capture reaction, what detector type might that occur for? It might capture a helium-3 detector, germanium, an inorganic scintillator, or even a capture-gated scintillator. Inelastic scattering is going to occur mainly in these organic and capture-gated scintillators. Elastic scattering, mainly the organic and capture-gated scintillators. So those sort of give you an idea of what you want to model. For MP post, the existing capabilities are calculate the response type for several common detectors like organic scintillators, inorganic scintillators, and helium-3 detectors. You see one organic scintillator here. It's quite pretty. It fluoresces when you shine a blue light on it. An inorganic scintillator that's totally packaged with a detector readout and a helium-3 detector on the bottom. We can produce pulse height distributions, which I've described already. We can look at time of flight distributions, which pulls up more information from those collision files I described earlier. And we can look at multiplicity, which is a function of fission, where fission can produce multiple type or photons and neutrons and multiple of them at the same time for a single event. Yeah, nice, Stephen. So I saw an answer in the chat, in the Q&A, that Stephen was saying, answering the previous question. So if we go back to the F8 tally, why would we see an interaction above the maximum Compton scatter deposition? The reason is we have a large volume detector. So in a single pulse that we're modeling here, even within an F8 tally, we can see multiple Compton scattering interactions. So there's going to be a certain time window that this F8 tally might resolve, or your MP post processing might resolve, that could occur or could observe multiple Compton scattering interactions. So if you have one Compton scattering, that's a maximum energy deposition, and then a subsequent Compton scatter that it's a fraction of that, you would see a higher pulse height than that single maximum Compton scatter event. A Compton scatter is not a terminating event. It's not a capture event. So the particle will continue after it Compton scatters, and that's why you would see these interactions above the Compton edge. Thanks, Stephen. So these are just some of the outputs you might see from that collision file. We can compare again the pulse height spectrum, which we've described earlier. That's in the center here. We can get even more in depth, and we carry out these time of flight experiments by measurement, where we look at these fission sources that produce both photons and neutrons. These photons are going to travel at the speed of light. So you can see this first peak here, it's time against frequency. And photons are going to travel quite fast during whatever geometric separation is. They travel at the speed of light. So we should see them in the time we would expect from a photon traveling at the speed of light. So if it's a meter, it's going to be something like a few nanoseconds. And the corresponding neutrons, unless they're extremely energetic, we're talking like 20 MeV, which most from fission are not, they're going to behave by classical mechanics. So it's just E equals half mv squared. So you can derive the velocity just from the neutron energy classically. And we'll see much longer times. In this case, we see a peak around 50 nanoseconds, which has several other things involved. These neutrons can directly fly from detector to detector. They can bounce off something in the room and then be detected in the coincident detector, although that is less likely. But we're trying to do this to figure out the energy of the neutrons from our neutron source. And we can use the photons as a benchmark to normalize our time of flight in case there's some sort of time delay in our system. We can model this in simulation because we can model time, as we showed in that collision file. So we can directly replicate the organic scintillator response we might see for a time of flight experiment. We can also look at the multiplicity. So californium has a very high multiplicity. This here is not the traditional multiplicity you might see, which shows an average emitted multiplicity of 3.57 neutrons per fission from californium. This is the detected multiplicity, which I believe is from a helium-3 detector. So it actually detects more than what the average is from californium because it has so many detectors and it's so efficient. And it has a very large timing gate. So the timing gate might be observing multiple fission events from a single californium. We can also create other correlated curves, and these just show phi and y of californium and some other different scenarios. The last thing I want to go into here is other information we can get from the collision file, which is the organic scintillator light output. I talked about pulse height, and I talked about equivalent energy response. When we have a detector measurement, gamma ray interactions are fairly straightforward. They directly scale. These neutron interactions and measurements have a quenched light output when compared to gamma ray light output, which is important for organic scintillators. They're a dual particle detector. So we need to be able to relate what a neutron light output corresponds to when we're trying to interpret neutron energy. This time of flight experiment makes it quite easy. We know the time of flight between the detectors, so we know the velocity and then we know the energy. But you might be restricted to a single detector, which in measurement only leaves you with the light output. You don't actually know what the incident neutron energy was. But you can relate that to what an equivalent energy gamma ray might produce. When a neutron interacts in an organic scintillator, if it interacts on hydrogen, it can deposit up to its full energy. You can have a purely elastic scatter wherein the neutron deposits all its energy onto a proton. But a carbon is a much larger element, has 6 protons and 6 neutrons on average. So it cannot be a full energy deposition. If it's an elastic scatter, it can deposit up to about, I think it's 60 or so percent of the neutron energy. So it will be slightly quenched there. And also the subsequent de-excitation mechanisms of the carbon inside the organic volume will reduce the light output. So we have these relations that we can apply to our simulations using MP post. The light output for gamma ray interactions on electrons is 1:1. It is our benchmark. So if there's a 1 MeV energy deposition for a gamma ray on an electron in our organic scintillator, it would produce 1 MeV EE, or electron equivalent of light. For a neutron of equivalent energy, as I mentioned earlier, and you can see on this curve, it's going to interact with a proton most of the time, and that's mostly what we'll see. So that's what we show on this plot. And that's going to be quenched. And we can derive these empirical relations to fit measured data when we're interpreting light output, which we derived from these time of flight experiments I described previously. And these empirical terms, we show a polynomial or a quadratic polynomial here. We can go into even more intense physical relations that include the stopping power, like the Burke's relation, but this is a more simplistic example here. When we apply this relation, we would scale our simulated neutron energy depositions by this light output according to the deposited energy. If we had an interaction on carbon, they're quite quenched, and the light output is going to be so much lower that we don't consider extremely complex models. We just have this linear scale, which is about 2% of the energy deposited will cause light output relative to the electron equivalent light output. Here's sort of a visualization of what the light output ends up being for these different interaction modes. All of them show a neutron that deposits 1.5 MeV of energy. And this is in a very large liquid scintillator, a 10 by 10 by 10 cube. This this large liquid scintillator has several interaction modes. If you had not a 1.5 MeV energy deposition, but a 1.5 MeV neutron can produce these spectra. If it's a single hydrogen scatter, you can see this red curve here, which looks a lot like a completely uniform distribution for the neutron. That makes sense. Elastic scattering on a proton has a uniform probability across all energies. If we had a double scatter, it starts to prefer higher energies, which makes sense because we're scattering twice, we're depositing more energy. If we had a triple scatter, we again see preserving higher energies. And these are all integral normalized, so it's not completely reflective of the relative rates between each case. It just is reflecting the shape. The single carbon interaction, we talked about 2%, right? So we're not even discretizing enough to see what the distribution would be. We just have this one data point at 0.02 MeV. The double carbon interaction, may follow this red distribution here. Again, we're not discretizing enough to see what the full shape is, but as you can see, it's much less light output than the corresponding hydrogen interactions. And if you had a triple carbon interaction, again, quite similar, except it slightly prefers the higher energy. So these are points I want to emphasize. It's quite complex to model your detector response, but we can model organic scintillators with MP post. We've shown it quite thoroughly in several experiments. And I hope this gives you a little bit of insight into what the pipeline looks like. I can't fully explain all of detector modeling in one lecture, but happy to take any more of your questions. And I do provide some resources at the end of the slides here, like the user manuals, the Polimi manual, JANT4 download, and of course, always refer to Noel if you're ever curious about any question related to radiation detection. Thanks so much. Ricardo, are you still there?
Yes, I'm still here.
Okay, cool. I just wanted to open the floor for Q&A. Anyone that would like to ask questions, please do. I think we asked some good questions along the way, so if you don't have any, I won't be offended, but happy to stay online for a bit and answer any of your simulation questions that you might have or detector response simulation modeling. I see John Langley raised his hand, and I see William. William, I'm going to go to John first since you've asked a few questions, but then we'll come back. But yeah, I see John raised his hand. I'm going to see if I can let you unmute. Yeah, go ahead, John. Okay, there we go.
Hi, Flynn. Sorry, not a question, just about the shake. The idiom comes from the two shakes of the lamb's tail being the a quick time, and the Manhattan Project came up with that unit. Just wanted to.
Oh, the Manhattan Project came up with shake. Yeah. Hopefully that'll make the new Oppenheimer movie this Friday. But that's funny that that was used for the Manhattan Project. It makes sense. That's about when MCMP started. Thanks,
right.
John.
Same with Barnes. So.
Yeah, but Barnes I just thought was more of a fun unit. It somewhat scales to the atomic size. I'm not sure why shakes would be used on a physical level. But yeah, thanks. That's nice information, John.
Yeah, no problem.
Okay, I'll start out with a simpler one here. I see Sophia's is asking if I've worked with JANT4. Not directly. There are several other students that work with Professor Ivanovic here that have to do JANT4. Rest their souls. It is hard to compile, but it can definitely be useful if you have a very unique scenario that MCMP doesn't have the capability for. JANT4 is open source, so you can customize it however you would like. It is very hard to get your hands on the MCMP source code. So if you have a specific experiment that's quite exotic, like what they carry out at the Large Hadron Collider at CERN, then you may want to come up with your own custom transport code, which JANT4 is definitely the preferred code for custom applications. But yeah, if you have a more specific ones, PS, please ask. Otherwise, I'll dismiss this question. Yeah, so I'm going to go with William's question now. Oops, sorry. I did not mean to do that. Hold on. Let's see. Williams an undergrad. Comparing homogeneous, spherical, and cubical radioactive sources. What specific emission pattern should the cube? William, you're asking quite a specific question here about cubic versus spherical anisotropy. If we had a homogeneous spherical source, I would expect that to be isotropic as long as your original source is isotropic. So like for a fission source, that's anisotropic. So if you had a spherical fission source, that would exhibit anisotropy. But if you had just like a large sphere of maybe cesium, which would be crazy if you did, but let's say you did, that should still have isotropic behavior because the radioactive source itself, the single particle that decays, is isotropic, essentially. One specific, if you had a cubic source, I can't quantify how that would affect the anisotropy isotropic behavior immediately, but because it's not in, a sphere in itself is an isotropic shape. It has a smooth surface and it's equally distributed in all directions. Where a cube, if you're trying to define radial space for a cube, that is not evenly distributed in space. It has sharp edges, which if you're talking about like self-shielding for a radioactive source, that would start to affect your emission from the end of the cube. Now, to get around that, you can, if you had like a cube of cesium, you could model that source so that the cesium continues to emit isotropically, but it's distributed inside this cubic volume of cesium. So the cesium is going to self-shield itself, and what actually gets outside of the cube will have an anisotropic behavior. So I think that fully answers your question. Thanks, Will. Lots of source definition. Is there anything on detector response that people want to ask? I see Modu ask if I could tell him more about simulation curve of efficiency in gamma spectroscopy. Yeah, I don't think I really included efficiency response curves on this lecture, but if we go back here where we model the random walk, this random walk will actually sort of capture what your efficiency is for your detector. The microscopic and macroscopic cross sections are interaction probabilities, and if you correctly model your detector volume with the correct compounds, elements, isotopic ratios, your simulated efficiency should be quite close to your measured efficiency. Not everything's perfect. It's hard to model an experiment exactly in simulation space, but as long as you use the correct cross sections, you should come quite close. There may be other factors like the conversion efficiency of your readout electronics, and then maybe you missed something in the geometry or your measurement was slightly off. Those are just some things that can interfere. Yeah, please, any other questions, or else I think we'll probably end early here. But yeah, please, another one in the Q&A. Please feel free to raise your hand as well. I saw on the graphs on the x-axis, the units are in MeV. Yeah, so we went into this a little bit earlier, James. I'll quickly answer that one. With an organic scintillator, the light output for a neutron interacting in the detector is quenched relative to the light output of a gamma ray interacting in the detector. A gamma ray will scatter an electron and cause an associated light output from the excitation of that electron, the slowing down of the particle in the volume. if a neutron scatters on a hydrogen, it will produce a charged proton, which then slows down in the detector. Both produce light, but the proton light output is quenched relative to the electron. So we quantify this light output relative to the same light output of an equivalent energy electron. So it is the MeV, mega electron volt, electron equivalent light output. It's a very relative term, but it's useful when we want to go back and quantify the energy characteristics of, say, a fission source. And we want to know a little bit more about the energy of those neutrons, because the electron energy is 1-to-1, but the neutron light output is nonlinear and quenched. So we have to have this relative metric. Good question. Is it possible to model multiple sources with different intensities and energies? Definitely. Yeah, I was hoping for a little bit more on questions on detector response, but that's fine. We can keep talking about sources. Yeah, you can get quite detailed with a source definition in MCMP. Yeah, you could model an entire reactor in MCMP, which has a litany of different sources. But it's all, problem truncation is important as well. If you simplify your simulation, but it's still detailed enough to model your experiment, that's the best scenario, because your simulation will not take as long, and it's not as much to debug. But yeah, you can become quite detailed. Okay, thanks, Stephen. It's nice to have you online, helping with the Q&A. He says for shakes that it is an acronym in reference to stoichiometric. I think stoichiometric is what you meant to say. Measure with respect to hysteresis probability and kinetic energy. Oh, interesting. Yeah, so that brings in several concepts like hysteresis. But yeah, if you want to learn more about shakes, which I'm sure I will after this lecture, make sure to look it up. I don't know if Stephen, if you got that off the top of your head or you were looking that up, but I appreciate your answer. Cool. Yeah, if there are no other questions, we have 3 minutes left. I could take one more if anyone wants to raise their hand or put one in the chat. Otherwise, I think we will adjourn. Be all a minute to respond. Yeah, with that, I think it's a good time to end. But thank you so much for attending today's edition of the nuclear. Oh, we have 2 more questions. There we go. Okay, I think there's a name there. Courtney, if you could take care of that, I'd appreciate that. Abhishek, can you help with installation of MCMP softwares? No, but the MCMP software should come shipped with an HTML file that will walk you through that installation. So if you ever have issues, you can maybe reach out to RSIC. They're not super responsive, but the folks at Los Alamos National Lab have a support group as well for MCMP that I think is a bit more responsive. If you're still having trouble, please reach out. I can try and give you that email. And then Abhishek says he's used OpenMC. That's great. A bit irrelevant. Is OpenMC. Oh, sorry, I'm looking at old questions. Yeah. Debug time. Okay. Sorry, I was looking at old questions there. William. Okay, so these are a bit quick questions, and I think we'll then adjourn. William was asking, is debug time usually more important than simulation time? It really depends on what your scenario is, your deadlines regarding that. Yeah, it's fairly subjective. What's more important? A lot of people that work in science are a bit of masochists and want to make an excellent model, which is a great endeavor, but sometimes that can cause issues with deadlines. So yeah, it's a fine balance. Asma asks, what is the boundary condition for MCMP? It's whatever you define it. Yeah, I'd need a little bit more specific than that. What's your scenario for what you'd want your boundary condition to be? But typically, you have an experiment that you want to model, and you know what will affect your experiment. So your boundary is the point where you think modeling will not have any further effect on whatever experimental output you're trying to model. But yeah, thanks everybody. I'll go ahead and end the lecture there. And thanks so much for attending. Tomorrow we will have Dr. Chris Perfetti, and he will be talking about nuclear data benchmark evaluation. And this is quite relevant to a lot of this transport and simulation that we've been doing the past couple of days, and gives a national laboratory motivation and perspective on all these transport simulations. So we look forward to seeing you all online tomorrow. Thank you.